What we are going to talk about today is some common negative feedback op-amp circuits. So the first one that we are going to look at is this guy here. Where I am going to apply my input signal Vn to the non-inverting input. I'm going to have a feedback loop here, which may or may not contain a resistor. So I'm just going to put one here. It actually doesn't matter whether that resistor is physically there or not. We'll talk about that in a moment. And for all of these, we are going to implicitly assume that the circuit is supplied with enough power to make it behave in the way that I'm describing. Okay. So to analyze these circuits that we talked about today, again, all being negative feedback circuits, we're effectively going to go through the same few steps over and over again. We are going to apply the op-amp rule that says no current can flow into or out of our input terminals. Then we are going to determine the voltage present at our non-inverting input terminal. We are next going to apply our ideal op-amp rule that says that no voltage drop can occur across my input terminals. We will then apply Kirchhoff's current law at our inverting input terminal node, and then use that relationship to determine what our output voltage V out is. So in this case, we know that this current is 0 amps. And this current is 0 amps, since no current can flow into or out of our op-amp's input terminals. From that, the voltage present at our non-inverting input terminal must simply be Vn, right? Applying our op-amp rule that says there can be no potential difference across our input terminals. That means Vn also appears at our inverting input terminal, V minus. Okay. So if we apply Kirchhoff's current law at our inverting input node, what we have is V minus V out divided by the value of this resistor R is equal to 0, which implies that V out is the same as V minus, or V out is exactly identical to V in. If that resistor R weren't there, Kirchhoff's voltage law would give us the exact same relationship. So this is an example of a unity gain buffer amplifier, okay, where our voltage gain, AVCL, is the ratio of V out divided by Vn, which is exactly equal to 1. So it's called a unity gain amplifier. It behaves as a buffer amplifier by effectively presenting a infinitely large input impedance while maintaining the characteristics of the signal as it transfers it from the input to the output. So this is very infrequently used as an amplifier itself, but it's used as a stage in cascaded amplifiers where effectively the input signal isn't able to provide enough power. So the power comes from the op amp while carrying the signal quantities from the input to the output. Okay. So if you had something like a sensor that was running off of using a piezoelectric crystal to convert some sort of mechanical deformation into an electrical signal, that does a good job at creating voltages, but a pretty terrible job at creating the associated currents as well. So you would just amplify the voltage signal using a unity gain buffer so that any necessary current to deliver power to the output load would come from the power supply itself instead of the sensor in question. So again, this guy is called a unity gain buffer. The next circuit that we are going to analyze is going to look very similar. And in truth, the unity gain buffer amplifier is actually a specialized case of this guy. We are again going to apply our input signal directly to the non-inverting input node. We are going to have that feedback path connecting the inverting input terminal to the output terminal. I'm going to call this guy resistor R2. We're going to measure our output voltage here. And again, we're working under the assumption that our device is powered. So the big fundamental change here is instead of having an open circuit, we now have a resistive path to ground. So if R1 were infinity, it's exactly the circuit that we had before.
Pardon me, that first configuration is called a UC.
Yes. Right.
Well, that's what I didn't make sure.
Yep.
Name.
Yeah, no, that's the name of the circuit is a unity gain buffer. All right. So we're going to apply those exact same op amp rules here. Zero amps can be flowing into our input terminals like so, which means the voltage present at our non-inverting input terminal is again Vn. And because of our second op amp rule, or the op amp rule that states no potential difference can occur across our input voltages, that same voltage appears at the inverting input terminal. Right? Applying Kirchhoff's current law at the inverting input terminal gives us Vn over R1 plus Vn minus V out over R2 is equal to 0. And with a small amount of mathematical manipulation, we will find that V out is equal to 1 plus R2 over R1 times the quantity Vn. So we have a closed loop voltage gain of 1 plus R2 over R1. This is called a non-inverting amplifier. So in a non-inverting amplifier scheme, we're going to talk about briefly why it's called non-inverting. There's really two principal reasons, which are kind of the exact same thing, but expressed in different ways, okay? So the first reason it's called a non-inverting amplifier is because the input signal is applied to the non-inverting input term, okay? The second reason it's called a non-inverting amplifier is because if the input signal is a positive quantity, the output signal must also be a positive quantity. So this device does not invert the polarity of the input signal. That's the whole point of the non-inverting input term. Okay. Now we can observe a couple of things here by looking at either our input-output relationship or our closed loop voltage gain for this circuit. It is impossible for us to get a voltage gain that is less than 1 in this circuit, right? So if R1 is much, much larger than R2, our gain approaches its minimum value of 1. In practice, though, we will see that the voltage gain will always be greater than 1. So this amplifier can only amplify signals or make the magnitude of the signal larger. Okay. Let's see. I think that's really the only things I have to say about this guy in particular. We have our voltage gain equation. We've talked about its inability to change the polarity of the signal, and it can only make signals larger. All right. Our next circuit is going to again be extraordinarily similar. So we're going to have our negative feedback path containing our resistor R2. We're going to have that exact same resistor R1, but now what we're going to do is we're going to apply our input signal at that open leg of R1, and we are going to ground our non-inverting input terminal. So let me scroll up here just real quick. The fundamental difference between these two circuits is that we are taking these two voltages and swapping. Otherwise, they are completely and utterly identical. Since this current must be 0 amps and this current must be 0 amps, the voltage present at our non-inverting input terminal is 0 volts. And so 0 volts occurs at our inverting input terminal as well. So this circuit uses what's called a virtual ground, right? And I say that because the inverting input node is acting like ground for this circuit, despite the fact that there is not a physical connection to ground. Okay? If we apply Kirchhoff's current law at the inverting input terminal, we get 0 minus Vn, so negative Vn divided by R1 plus 0 minus V out, or negative V out divided by R2 is equal to 0. And with a little bit of algebraic manipulation, we find that V out is simply negative R2 divided by R1 times Vn. And therefore, we have a closed loop voltage gain. V out over Vn is simply negative R2 over R1. This is an example of an inverting amplifier. Where, again, that name comes because of two reasons, which are effectively the same. Our input signal is applied through our resistor network to our inverting, and we can see that for a positive voltage VN, our output will be a negative voltage. So we are inverting or changing the polarity of our signal. Now, this type of amplifier can be used to both increase or amplify an input signal or decrease or attenuate an input signal, okay? So we have the option of making our output signal larger than our input or smaller than our input if needed. But this increase in functionality comes at the cost of changing the polarity of our signal, which we could always change right back by just adding a second stage with a gain of 1 or negative 1 if we were so inclined.
Like a negative unity gain buffer?
No. Well, yes. If R2 will equal to R1, the gain would be exactly -1, right? But it doesn't. I would not call that a negative unity gain buffer because it does not present an infinite input impedance to the input signal. Right, so there's a difference between having a gain of 1 and being a unity gain buffer. And a large part of that is the really, really large input resistance. So based on the analysis that we did last Friday, where we analyzed effectively this exact circuit, the input resistance seen by our input signal is going to be very close to the value of R1. So if we want a very high input resistance, we have to choose a very large resistor. But if that large resistor that we choose is on the order of the input resistance of the op amp itself, that starts messing things up. So there's a limit to the input resistance that we can get with this without changing the behavior of the circuit. All right. Yep, absolutely. Yeah. I don't know what you mean by put it in backwards. Okay, yeah, no. So if we put the feedback loop on the positive terminal, we would be guaranteed to not have a unity gain system because a positive feedback is going to force our output to go to VCC plus or VCC minus, right? So if we had put feedback on the positive, let's go back here real quick. If we flip the op amp over, where the feedback loop is connected to the non-inverting input terminal, this would be an example of a negative or an inverting Schmidt trigger, right? Or a positive feedback circuit. Similarly, if we flip this guy around, that would be an example of a non-inverting Schmidt trigger, which we've already done, right? But we cannot arbitrarily change. Positive feedback and negative feedback do very different things. Yeah, so we get very, very different output behaviors. All right, so here are our kind of generic amplifiers. Now let's talk about some with more specific purposes. Okay. So got my generic op amp that is powered. I have negative feedback. Again, for all of these examples, I will have negative feedback, which is what's allowing me to use my ideal op amp rules. I'm taking my output voltage at my output pin, and this time I'm just going to call resistor R when giving it a number designation. You'll see why in a moment. And again, I'm going to ground my inverting input terminal. And what I'm going to do here is I'm going to apply multiple resistors. So let's call this guy up here R1. Let's call this guy right here R2. Let's call this guy right here R3. And at the other leg of resistors R1 through 3, we're going to have VN1, VN2, and VN3. So we have multiple input signals and a single output signal. And all of our inputs are applied on the inverting input terminal side of the op amp. So we should expect to see a negative output if VN1, VN2, and VN3 were all positive signals. Okay. So for our analysis, we're literally going to do the exact same thing. We know that this current is 0 amps. We know that this current is 0 amps. By inspection, we can see that the voltage present at the non-inverting input terminal is 0 volts, which means the voltage present at the inverting input terminal must also be 0 volts. So applying Kirchhoff's current law at our inverting input terminal gives us negative VN1 over R1 minus VN2 over R2 minus VN3 over R3 minus V out over R is equal to 0. And from this, our output voltage V out is simply negative R times VN1 over R1 plus VN2 over R2 plus VN3 over R3. We can't really define a voltage gain for this system because we don't have a single input versus single output relationship. So let's talk about what's going on, okay? This amplifier is what's called a weighted inverting summer. I'll write that down. And its name describes exactly what's going on, okay? So it's an inverting summer because of the negative sign, right? Or all of the inputs are applied on the inverting input terminals, okay? It is a summer because it's adding up our input signals, and it's weighted because it's scaling those input signals by a factor of negative R over the resistor that the input signal sees, okay? So that means that the quantity VN1 is scaled by a factor of negative R over R1. The quantity VN2 is scaled by a factor of negative R over R2. And obviously VN3 is scaled by a factor of negative R over R3. We can realize this circuit with any number of input signals that we want, right? We don't have to limit ourselves to 3. It can be 2, it can be 15. We just have to make sure that all of our signals are applied on the inverting input side, okay? So Trying to think of an application that would use the weighted inverting summer. One isn't jumping out the top of my head right now, but let's talk very briefly about a non-weighted or just inverting sum. Okay. So if R1, R2, and R3 are all equal, that means that each individual input signal is getting scaled by the same factor. Okay. So that type of configuration is actually used a lot. If you consider a weigh station, like one that weighs trucks and all that kind of good stuff, okay? You would use an inverting summer to measure the output of all of the load cells so that you would just scale the weight seen by each axle by an appropriate amount, right? So if a load cell, let's say that it converts 1 ton of weight on that load cell to be an output voltage of 1 volt. Each one of these input signals would be representative of the output of each of those load cells that measures the weight seen at each axle. And then it simply adds them all together and tells you what the total weight of the vehicle is. Where you can set your weight conversion by your resistor values. So you could literally use resistor values to give you your answer in kilograms, metric tons, imperial tons, whatever you wanted, all by choosing your resistor values specifically for however your load cell particularly converts weight into an electrical signal. That's kind of classic example of an inverting summer. I guess a weighted inverting summer, if I were feeling really, really squirrely, I could compute your final grade in this course using an op-amp circuit, where since your exam 1 grade is 20% or whatever, your exam 2 grade is 20%, I could literally do that using voltages, but Excel makes it much, much easier. So anyway, so if for whatever reason you need to scale things by different values, use a weighted inverting summer. If you want to scale everything by the same value, just make R1, R2, R3, etc. have the same value. Now, we're not going to analyze this, but it is possible to make a weighted non-inverting summer simply by applying all of our input voltages on the non-inverting side. The problem with that is that the scaling factor gets real weird real quick, especially if there are more than 2 input signals applied. Okay? So it's physically possible to construct something that works that way, but it is way less straightforward to understand the relationship between choosing your resistors to get the expected output. It is actually much easier to make a weighted inverting summer and then invert that signal using an inverting amplifier to make your output a positive voltage than it is to just design it to give you a positive output in 1 gate. So, absolutely possible, very little practical application because of how difficult it is to get the scaling correct. Connor.
If you're going to apply a single resistor value to 1, 2, and 3, why do you even need those resistors? You just use the same value in R's place and get the.
Okay, so if we didn't have resistors here, if we just applied these directly, we have a little bit of a problem. Because the voltage present at our non-inverting input terminal is 0, and the voltage present at our inverting input terminal would be multiple values, right? The resistor has to be there in order to accommodate having different input values. It also has to be there because we would be applying a very large differential voltage directly to the input terminals, right?
That's
So
kind of my question, like what happens?
the output saturates the VCC plus or VCC minus because it's no longer behaving like a negative feedback amplifier, right? Yeah,
So R1, R2, and R3 are all going to be exponentially greater than R, right?
it depends on what you want to do. So, for example, if you want Vn1 to be scaled by a factor of 1/2, then R1 needs to be half as large as R. If you want Vn2 to be scaled by a factor of 5, then R needs to be 5 times larger than R2. If we looked at this circuit using superposition, this is nothing more, can't look at it at the same time apparently, than this circuit, except with only one input on at a time. So the output of that weighted inverting summer is just this relationship for each of the inputs added together. So we can make our output signal smaller for each input or larger for each input, just depending on the ratio of the resistors that we choose. Does that make sense? Okay. I was thinking about illustrating that with an example of making a 4-bit digital to analog converter, which is actually one of the design problems that you're going to have an option to do, but it would take a little while to do. I'll leave it up to you guys to choose to do that. But Logan, if you want to ask questions at the end, I don't mind talking about it now, or if you want to wait and we flesh it out and make it make sense, I'm happy to do that too. Okay. All right, so all right, so we're going to have a basic op amp. Here's VCC plus. Here's VCC minus. We have negative feedback. I'm going to call this resistor R. We're going to have another resistance here having the same value of R. And then on the inverting input side, I'm going to apply, excuse me, the non-inverting input side, I'm going to apply a resistor network as well. All right. And let's call the voltage applied on the non-inverting side V1 and the voltage applied on the inverting side V2. Okay. So what this guy is, sorry, what was that? All of them, yes, all of them have an identical resistor value. We can talk about what happens if they don't once we get through this analysis. Okay. This circuit looks like a non-inverting amplifier and an inverting amplifier at the same time. Okay. And so what I mean by that is, generally speaking, V2 sees an inverting amplifier, right? The input voltage V2 is applied through that resistor at the input of a non-inverting, excuse me, an inverting amplifier. V1 applies a voltage through this resistor network that is going to see effectively a non-inverting amplifier. Okay. We have two different ways that we can analyze this. One is using superposition. The other is a direct approach. Which way do you guys prefer? The direct approach. Okay. So we know that this current is 0 amps and this current is 0 amps because our ideal op amp rules tell us so. So the voltage present at the non-inverting input terminal. This one, we cannot directly say it has a particular value because we have this resistor network applied, right? So this resistor network here is acting on input voltage V1 to produce a voltage V plus that is applied at our non-inverting input terminal, okay? So anybody care to take a crack at what that voltage V plus is going to be? Exactly right. 1/2 of V1. So this is a simple voltage divider network. And we can treat it that way because we know that no current is able to branch off and flow into the input. So this input voltage V1 just sees 2 resistors R in series, and we're looking for the voltage drop measured across this resistor. Yes, sir. We can call it KCL, we can call it KVL, or we can call it voltage division, all kind of the same thing. Yeah. So applying Kirchhoff's current law, any voltage that's supplied by this voltage source, excuse me, any current leaving the positive polarity terminal of this voltage source V1 would flow through this resistor R, and then all of that current has to flow through this resistor R because none of it can branch off. So V1 would be equal to I times 2R. So the voltage drop over only one of those resistors, because the voltage here is, the voltage at the non-inverting input terminal is a nodal voltage, meaning it's measured at this node with respect to ground, is the same as the voltage drop over this resistor R. So that's why it's exactly 1/2 of V1. That is also the voltage we observe at the inverting input terminal, right? So writing a KCL equation at the inverting input node, we have 1/2 V1 minus V2 over R plus 1/2 V1 minus V out over R is equal to 0. Right? So the current flowing to the left plus the current flowing to the right equals to 0. We can multiply both sides through by R, and that'll give us 1/2 V1 plus 1/2 V1 minus V2 minus V out is equal to 0, which tells us V out is simply V1 minus V2. So this is an example can't spell it, differencing amplifier. So if we had 2 input signals and we wanted to know what the difference between them was, this gives it. And then if we wanted to scale it, we could either play around with the resistor values to force scaling to happen, or an easier thing if we want that difference to be scaled by a common factor would be to take the output of this and put it into an inverting or non-inverting amplifier, depending on what we want. Bradley.
If needed, could we combine that with the integrated summer where we have like multiple inputs on the inverting terminal and multiple inputs on
It would be, So there's nothing to stop you from physically trying to implement a scheme like that. The problem there is the complexity of the math involved, okay? And so what I mean by that is this guy works really nicely because effectively what's happening here, this resistor network takes V1 and divides it in half. That half V1 then sees a non-inverting amplifier that has a gain of 2, right? Because it's going to be 1 plus R over R, or 1 plus 1. So this signal gets divided in half and then multiplied by 2 to give us V1. This signal sees a gain of -1, and so that's where this minus V2 comes from. As soon as we start adding other things to it, we do not get that simple relationship anymore, right? Yeah, so there's absolutely nothing preventing us from tacking on other resistors all over the place and other input voltages, either on this side or this side, but I can practically guarantee that it's not going to have such a simple input-output relationship.
When you try scaling the resistors there,
It gets ugly real fast.
it's not exact.
So if this resistor, if these two resistors weren't the same, then this input voltage, instead of it having exactly a 1/2 relationship, it had, let's say that this one is 2 and this one is 3, right? Then we would see 3/5 of V1 gets applied here instead of 1/2. Like it's all set by the ratio of the resistors there, right? So having equal resistors makes sense here because we're scaling by 1/2 and then scaling by 2 to get our original signal to the output. And then this part just subtracts that from the output as well. But as soon as we start having non-equal resistor values, it starts getting real wonky, real fast. Yeah. Not saying you can't do it, but it's hard mathematically to choose things well to make it get a nice simple result. Sure.
Why don't you do like 3V1 scale where it's
Yeah, so if we wanted to do 3V1 minus V2. 3V1 minus V2. No, I'm just thinking about how we would do that, because inherently the voltage divider at the non-inverting input terminal side is going to give you a smaller result. So making V1 larger, the most obvious thing to do would be to have V1 go through an amplifier with a gain of 3 and then and chain that to be here, as opposed to trying to do it with these resistor values. Now, if you wanted to do like V1 minus 3V2 or something like that, that's a little bit easier to figure out because that would be established by these up here. Right? But you can always do all of this with just chaining multiple things together, which is what we're going to talk about on Wednesday. Yeah. All right, let me find my stylus. Here we go. Okay, so to this point, we have talked about making signals larger, making signals smaller, adding signals together, taking the difference of signals. The last two mathematical operations that we can employ with single op amps are differentiation and integration. Okay, so we can do calculus as well. So this will be our first example. We are going to ground the non-inverting input terminal, we are going to apply negative feedback. And instead of having a resistor in the feedback path, we are going to have a capacitor C. I'm going to draw this a little bit better to give myself more room. Okay. Then over here, we'll have our resistor R. And for this to do anything useful, our input signal now needs to be time varying, which will in turn generate a time varying output voltage. So before we analyze this, and we're going to do it in effectively the exact same way that we have done all the other circuits, we do need to refresh ourselves on the current voltage relationship for a capacitor, right? So recall from circuits 1 that the current flowing through a capacitor, IC of t, can be expressed as C dV by dt. And the opposite relationship, capacitor voltage Vc, is 1 over C times the integral of IC as a function of time, where I'm using X as a dummy variable for time here, since variable T shows up in the bounds of my integral. So, all right, so let me think. We know that this current is 0 amps, and we know that that current is 0 amps. We know that V plus as a function of time is 0 volts, which means V minus as a function of time must also be 0 volts, right? So let's define this guy as the voltage drop across my capacitor. And in turn, this guy as the current flowing through my capacitor. Okay. So we're going to apply Kirchhoff's current law at our non-inverting input terminal, but we're going to do it a little bit differently than how we've done it previously. Okay. So what I mean by that is, instead of saying this current plus this current is equal to 0, we're going to say this current is equal to this current. Okay. Seems like an arbitrary decision, but I promise you it's going to make the math a little less wonkified here. So what's the current flowing from left to right through the resistor R? Exactly right. So from that, IC of t is given by Vn over R. 100% correct. Okay. Now, what's the relationship between Vc and V out? So Kirchhoff's voltage law tells us that 0 plus Vc plus V out is equal to 0, which means Vc is exactly equal to negative V out. Sorry, this thing will not write. So V out as a function of time is negative VC as a function of time, which is negative 1 over RC times the integral of Vn, where I've simply substituted this relationship IC is Vn over R into this integral relationship that tells us the relationship between the voltage drop across the capacitor for a known amount of current. Now, I am doing a little bit of hand waving here because obviously we're not really going to know what's going on at t is equal to negative infinity, okay? Right? More traditionally, we would integrate from t naught some point in time where the voltage drop across the capacitor is known to some later point in time, which would then in turn add an initial condition onto our relationship here, okay? How that's typically satisfied so that we don't actually have to measure capacitor voltage or anything like that is by, I'm going to do this in pink, placing a very large resistor in parallel with capacitor C. Okay. So effectively what that very large resistor there does is gives the capacitor a means by which to convert any stored energy into heat so that this guy always starts with an initial voltage of 0. Okay. Once you learn Laplace transform, we can actually analyze this circuit with this resistor in and see that it gives us this exact relationship as long as we choose R to be large enough. But for now, just understand effectively this part without the pink bit functions as an integrator, but it does depend on whatever the initial voltage drop across the capacitor is, which if you're trying to design a circuit or anything like that, just force it to be 0 on your simulation. All right, so again, this is an integrating amplifier. What's really interesting about this circuit and the next one that we're going to talk about, so in analog signal processing, this circuit fulfills the role of performing the mathematical operation of integration. Okay. In communication systems, this circuit fulfills the role of a high-pass filter. And in controls systems, this is a fundamental building block of what's called a PID, or proportional integral differentiating controller. This one circuit fulfills 3 different roles in 3 different aspects of electrical engineering. So I find that to be pretty dang neat. Okay. You will see this guy show up again and again and again, depending on what concentrations you take because of how versatile it is. The last circuit is the exact same thing as the previous one, except that we changed the position of the resistor and the capacitor. So here's R, here's V out, here's C, Here's Vn, like so. And here's Vc. Here's IC. So we know that this current is 0 amps. We know that this current is 0 amps. And from this, V plus is 0 and V minus must also be 0. We're going to apply Kirchhoff's current law at our inverting input node just the way that we did last time. So the current flowing in is IC over T. IC of T. And the current flowing out is 0 minus V out over R, or just negative V out over R. What's the relationship between Vn and Vc? They're equal. Not equal and opposite, just straight up equal, right? Vn measured with respect to ground, which is here, is the exact same thing as Vc. So since IC can be written as C dVc, which we know to be Vn, this tells us that V out as a function of time is simply negative RC dVn by dt. Right? Move the negative sign over here, multiply both sides by R. That's what I've got left. So this is an example of a differentiating amplifier, which in communication systems is used as a low-pass filter and is also a fundamental building block of automatic control systems. Okay. Differentiating amplifier. So we can absolutely realize differentiating and integrating amplifiers using inductors as well. Okay, but in practice, these are done using capacitors for a pretty legitimate reason, and that is the tolerance on a capacitor. So if you were to buy a capacitor from a pack, something like that from DigiKey, the tolerance of a capacitor is typically smaller than the tolerances seen in inductors, meaning that you're more likely to get the behavior that you want if you use a capacitor versus an inductor. Another reason that you see these capacitor-based circuits as well is that they are much easier to create using integrated circuits processes. Because if you're making an integrated circuit amplifier, forming a capacitor is very simple because you literally just put a layer of metal on top of another layer of metal and just make sure leads are coming out to apply your voltage, right? You can literally make a parallel plate capacitor by physically putting metal over another piece of metal. Making a coil in an integrated circuit is damn near impossible because all of your structures have to be planar. So you can make like a coil and then run things out like that, but the more turns and stuff like that you want in your coil to make your inductance larger means the more physical space that you have to occupy on your chip. So as I said, generally speaking, The practical realization of these circuits is always going to be with capacitors and resistors. On one of your homework problems, I'm going to make you derive things for an inductor, just because I'm mean, I guess. Bradley.
So does an integrated circuit mean that it's like flat fit on a chip? Exactly.
So an integrated circuit means that everything is monolithically integrated on a single substrate, typically silicon. Okay, so it's all integrated together. So instead of a discrete resistor that you would go buy from a store or anything like that, the designer has the opportunity to set aside certain areas of the chip, dope them in certain ways that they behave like resistors. Other parts of the chip are made to behave like capacitors. Other parts are made to behave like transistors and all that kind of good stuff. So it's not you go buy parts off the shelf. It is an integrated package that was designed by somebody to fulfill a specific role. So an op amp in and of itself is an integrated circuit.